In the last video, we understood that the operating system protects the system using isolation and trust boundaries. But now the real question is, when you open an app like a browser or a music player, what exactly is happening inside the operating system? Because security problems don't just exist in theory, they happen when the code is actually running. So in this video, we will understand what a process is, what a thread is, and why execution itself can create vulnerabilities. When you open an application, the operating system don't just run it. It creates something called a process. A process is simply a running instance of a program. The operating system gives each process its own memory, CPU time, access to the files, and unique identity. You can think of a process as a protected container where your program runs. Processes exist mainly for isolation. Let's say you have a browser, a password manager, and a game. If there was no isolation, the game could simply read memory from password manager and it steals all the passwords, and that would be a disaster. So the operating system ensures one process cannot directly access another process memory. And this isolation is one of the strongest security guarantees provided by the operating system. Now, here's something important. A process is not the smallest unit of execution. Inside a process, we have threads. A thread is basically a single path of execution. One process can have multiple threads running at the same time. For example, in a browser, one thread loads the web page, one handles user input, one plays the video, and one handles network requests. Everything feels smooth because multiple threads are working together. And threads inside a process share memory. And this makes things fast and efficient. But it also creates risk. Because when multiple threads access the same data, the result may depend on timing. And when timing matters, things can go wrong. And this is where race condition comes in. A race condition happens when the behavior of a program depends on timing. Let's take a simple example. A program checks, is this user allowed to access this file? And if yes, it opens the file. Now imagine this. Thread A checks permissions before the file is opened. Thread B changes the state. Now the system may open something it should not. The program assumed things are safe, but the state changed in between. And this is called the race condition. And attackers can exploit these timing issues. And by the way, race conditions are not just some interview theory. Real systems have actually been hacked because of them. One famous example is a Linux vulnerability called Dirty Cow. In simple terms, two processes were accessing the same memory at almost the same time. One trying to read it, while another trying to modify it. Because of this timing issue, attackers could trick the system into changing files that were supposed to be read-only and gain higher privileges. And this bug existed in Linux for years before being discovered, which shows how dangerous tiny timing issues can become in operating system. If you want to learn more about Dirty Cow, I'll put some reference in the description also. Now, programs are not static. They are constantly reading memory, updating values, switching between threads, and interacting with the operating system. When assumptions break during execution, unexpected behavior appears, and attackers look for exactly these situations. Because if they can control timing or memory access, they can sometimes bypass the security checks. And many people think crashes are just bugs. But in security, crashes are very important. A crash can mean invalid memory access, corrupted data, and broken logic. And if an attacker can control these situations, they may control the program itself. So a crash is often a signal, not just a problem. So basically today we learned a process gives isolation and a thread gives execution. But shared memory introduces risk like race conditions. And these execution issues can become real vulnerabilities. In the next video, we will go deeper into memory, virtual memory, stack versus heap, and why buffer overflow exists. And this is where things get even more interesting. So till then, stay safe. We'll keep it simple.